If you've worked through school as a hydrologist, you already know the pain of calculating water quality index values by hand. It's difficult and sometimes physically uncomfortable. I built the WQI calculator linked below to expedite the process. People have built similar tools in the past, but all the ones I found are either unable to calculate many values at once or simply sum up Q values. My calculator is different. I made an Excel file that allows you to input raw data collected from the field and automatically calculate the full WQI from those values directly. If you're just here to get the final number, this is all you ever need to see. This is the user interface tab of my spreadsheet. All you need to calculate your WQI using the National Sanitation Foundation's methods is fill in the spreadsheet. Then, without any need for the usual graphs or arithmetic, the spreadsheet will provide you with the WQI based on the information you entered. If you want to understand more about how this calculator works, you should first know what water quality indices are. A water quality index is an attempt to quantify in a single number how good a given sample of water is. There are dozens of WQIs in the hydrologic literature, but for my work, the National Sanitation Foundation's WQI is the standard. The NSF WQI was generated by asking trained hydrologists to rate individual samples on a scale. From their responses, graphs were generated for the 9 parameters deemed to be most important: biochemical oxygen demand, dissolved oxygen, fecal coliform, pH, temperature change, total phosphate, nitrate, turbidity, and total solids. WQI is calculated from these graphs. Water quality index values are useful in understanding how water quality changes over space and time, allowing long-term graphs to communicate the overall stability of aquatic ecosystems. WQIs are also useful when persuading policymakers to support environmental protections and best management practices. When you're a scientist working on a problem, your life is full of gritty details, but when you're talking to a layman, an abundance of line graphs is going to dilute your argument. Boiling it down to one graph to communicate your conclusions is the way to go. Getting back to methods and math, what you're normally supposed to do is take each of your 9 parameters for each sample, line up the value you measured for each parameter on the x-axis of its corresponding graph, and draw a vertical line at that point. Then, you record the y value of where your vertical line crosses the curve drawn on the graph. This y value on the graph is the Q value for that parameter. Then you repeat that process for all 9 of the parameters. Once you have all 9 of your Q values, you have to multiply each Q value by its weighting factor. Once you have your weight-adjusted Q values, you add them all up, and you finally have your WQI. This process takes forever and is prone to human error. Most automatic calculators will just take your Q values and generate a WQI, but it's obvious that the bulk of the work comes in generating the Q values to begin with. That's where this spreadsheet comes in. Using it, I was able to get about 100 hours worth of calculations done in just 30 minutes. With that said, let's move from the traditional methods to the math that makes up the meat of this code. This monstrosity is the Data Calculations tab. Don't worry, we'll go slow. For an example, we'll focus on a single Q value calculation, pH. Before any math can even start, we need to make sure that there's a pH value to use. If there isn't, the final weighting will be adjusted and pH will be ignored. This cell, the availability cell, is just checking the pH cell on the interface sheet for common abbreviations of not available. If any of these abbreviations appear there, the output of the cell will be not available. Otherwise, it will read available. This block of text could just appear at the top of the Q value calculation cell, but that would have made the formatting unwieldy and the debugging process more difficult. The first line of the Q value calculation cell is checking the availability cell. If the cell says not available, the output in the Q value cell is also not available and the code ends. Otherwise, it goes on to check if the pH value is within the range of the curve. The NSF has specific rules for each parameter. In this case, if the pH is less than 2 or greater than 12, the Q value is 0. If it's between 2 and 12, we have to find it on the curve. Now, I keep saying the word curve, but this obviously isn't smooth. It's a bunch of line segments. If we look at the endpoints of those line segments, we come up with this array. On the left is the X value, and on the right is the Y value. As you can see, the ideal pH for water is about 7.4. This forecast function holds the remainder of the code. As you can see, the third and fourth lines mirror the fifth and sixth lines. This is because these lines of codes first match the pH values in the array to the pH-QI values in the array, then they determine which 2 points the given pH value falls between. After that, the forecast function uses basic geometry to find the y equals mx plus b equation for this line segment, and plugs the given pH in for x, which solves for y. For more information on this function, watch the video on the screen now. Now that we have the Q value for pH, we need to multiply it by the weighting factor for pH, which is what this cell does. If there is no pH, this cell shows up as 0. From here, all the Q values are added up and divided by the total of the weight factors of the parameters that were used. This means that if we're missing 2 parameters, the calculator will automatically adjust the WQI and assume that those 2 values were nominal in their effect, as per the NSF WQI standard. Now, eagle-eyed viewers may have noticed that there are more than 9 columns on this tab. That's because I built in a little quality of life feature. Many researchers lack access to a DO percent meter, and so must calculate the DO percent from other, more easily measured parameters. In this case, I use the same array function I used to generate Q values to find the DO solubility of a given temperature. From there, it was easy enough to find the DO percent for a given value. If you'd like to download this tool, check the description below or go to www.rowanmccarthy.com. Additionally, if you'd like to see more from me, check out my channel, where I'll be posting more environmental science content, documenting evolutionary histories, prairie root pools, water monitoring programs, and so much more. Thank you for watching, and have a wonderful day.